Hello everyone. Uh, in this video, we are going to discuss about representations of Dirac Delta function, which is quite crucial in our quantum mechanics. So, standard Gaussian integral, or if we say before defining the delta function, we often encounter standard Gaussian integrals. In these types of evolution, uh, a general form with linear and quadratic terms in exponent is given by like this. Integral I equals to minus infinity to infinity e raised to power minus alpha x square plus beta x dx equals to under root pi upon alpha into e raised to power beta square upon 4 alpha. So we have done this in our previous video. Now Dirac delta function, a rectangular representation. Consider a rectangular function r sigma x centered at a position A. So let's say our r sigma x is defined like it is 0 for all the values of mod x minus a greater than sigma, and there is value between a minus sigma and a plus sigma for this x when it is 1 upon it will be 1 upon 2 sigma. So the total area under this curve is always normalized to be 1. So let's say if we integrate minus infinity to plus infinity, so r sigma x dx is 1. So here we have this uh, graphical representation of this rectangular function. Now, if we see this blue line, so here is the center line A. So A minus sigma 1 and A plus sigma 1. So we have this length here. If we see this length is 2 sigma 1. Okay. Now, the this height where this sigma 1 is written is 1 upon 2 sigma, which is mentioned here. So if it is a rectangle, so we know the area of rectangle, which is length into breadth. Now this length is 2 sigma 1 and this height is 1 upon 2 sigma. So when we multiply it, we get 1. Okay. So what if we reduce the value of this sigma? Okay, if I try to reduce the value of sigma, so this baseline will reduce. Let's say for this green line, uh, for this sigma 2 must be less than sigma 1 because its base is now reduced and height is increased. Height is increased so that area remain 1. Okay, further, this sigma 3 must be less than sigma 2 and must be less than sigma 1. So it means its base is now again uh, reduced and height is increased in this sense. So that this area remained 1. So as we reduce sigma, the rectangular become narrower and taller. So what if sigma tends to 0? So if we reduce the value of sigma, we obtain a Dirac delta function. So if sigma tends to 0 for r sigma x, we get a delta x minus a. So we will get a sharp peak. So when sigma tends to 0, we will get a sharp mm, rectangular shape thin to the line, and its area will be 1. So when multiplied by a continuous function, uh, this fx and integrated, it shifts out value at x equals to a. So this is one of the property of delta function. So now I want to repeat one thing, that this is one of the representation of a Dirac delta function, one of the many. Okay, so here now when we multiply when we multiply this Dirac delta function with continuous function like this and integrate it over minus infinity to infinity, so it shifts. Okay, so let us understand it. So now if we multiply fx and delta x minus a, so let's say this is fx, red line, and this is our delta function r sigma, where sigma tends to 0. Okay, now if we multiply it, so what we do here, that this red line, okay, so Dirac delta function is a 0 here, so it will contribute nothing. And this side from here to here, here also from here to here, Dirac delta function is 0. So this red line, this part of red line will contribute nothing. Now we are left with this part. Okay, so uh, now here we this is a little thicker, but for a Dirac delta function we find a peak here. So its width be like a. So we can just replace that value of a such that uh, it will become fa, and integration of minus infinity to plus infinity r sigma x, limit sigma tends to 0 become 1. So we will left with f of a. So this is the shifting property. Now, the ramp function approximation. We can approach the delta function through another path by defining a continuous ramp function. Let's say that is t sigma x. This function smoothly transitions from 0 to 1 over an interval of width 2 sigma centered at a. So here is the graphical representation of our ramp function. So if value of this x is less than a minus sigma or equal to this a minus sigma, we will get 0. Okay, and if you can see a slope here, so a minus between a minus sigma to a plus sigma, we have like this representation 1 by 2 sigma bracket x minus bracket a minus sigma bracket close. Okay, and here you can see it is 1. So for which value of x it is 1? When it is greater than a plus sigma or equal to a plus sigma. Okay, now uh, if you remember in our I think 11th or 12th class, we studied about the slope. What are the slope? So the slope are always that the derivative of dy upon dx, we say it. So now what if uh, we differentiate it? So differentiate it with respect to x, what we will get? 1 upon 2 sigma. Okay, so if you remember, 1 upon 2 sigma we had faced here, 1 upon 2 sigma. Okay, so I will mention it ahead. So we will just say limit sigma tends to 0, derivative of this t sigma x with respect to x is a delta function. So uh, we will just generalize it, but before that we discussed one more function, a Heaviside step function. So this function, as we take the limit sigma tends to 0, the transition interval of the ramp function shrinks to 0, causing an abrupt jump. This limit yields the Heaviside step function, and this is the representation of our Heaviside function. So you can see that uh, over here, uh, value of this hx minus a is 0, and there is discontinuity over here, and here its value for a greater than x is 1. So you can see we have established a relationship that if limit sigma tends to 0, t sigma x. So if you remember, that is for that previous function, we have a slope here, and now here is a straight line. So it is saying that if sigma tends to 0, so t sigma x changes to Heaviside function, Heaviside step function. Now it is quite easy if we differentiate it. So in next step, notice that the derivative of the ramp function t sigma x yields exactly the rectangular function r sigma x, which I already mentioned you, it will be like 1 upon 2 sigma. So by taking the limit as sigma tends to 0 on both sides, we derive the fundamental relationship between the Heaviside and Dirac Delta function. So this derivative relationship d upon dx hx minus a equals to delta x minus a, and if you remember, this hx minus a can be written like limit sigma tends to, here you can see limit sigma tends to 0 t sigma x. So let me show you t sigma x. So here t sigma x. So if this sigma approaches to 0, so we will have a straight line from here to here. You are getting my point? So it will become a Heaviside step function. So let us move ahead. So here is the representation, graphical representation, delta x minus a. Now, derivative of a function with, I think there is a mistake, and it must be derivative of a function, discontinuous function. So let's say, consider the function sigma x equals to e raised to power minus mod of x. So how can we define it? We can write it in piecewise form. So sigma x equals to e raised to power x when value of x is less than 0, and e raised to power minus x when value of x is greater than 0. So taking the first derivative, it is quite easy. First derivative of this ex will remain ex, but second derivative with respect to x, we can apply here chain rule, so we will get minus e raised to power minus x. Now, if you see the graphical representation of both these, sigma x and its derivative, so if you see here, it's a continuous function. Okay. Now, here, sigma dash x, so you can see here, this is not a continuous function. Okay. So, what we can do here, so we just do another derivative. So notice the discontinuity at x equals to 0, where the value of jump from +1 to -1. So there is discontinuity of -2. Okay. So there is some important rule regarding this discontinuity. Whenever a function has a discontinuity at a particular place, its derivative always contains a Dirac delta function. So where is the discontinuity? In delta, sigma dash x. So our Dirac delta function will be in second derivative of this sigma 2 dash, because discontinuity is in this function. So the second derivative of sigma double dash x will have a continuous part plus a delta term located at a discontinuity. So sigma 2 double derivative of the sigma dash x is continuous part plus delta x into whatever the jump we have seen in our uh, sigma dash. So the amount of discontinuity, which is a jump in sigma dash x at x equals to 0, is -2, which we already mentioned. So therefore, the full second derivative is sigma double dash x equals to e raised to power minus mod x minus 2 delta x. So here is the representation of delta function. This sigma double derivative of sigma, oh sorry, I was continuously saying it sigma, it is psi. So double derivative of psi x. So now let's move ahead and discuss about Gaussian representation of the Dirac delta. So another common representation of Dirac delta function is derived from the normalized Gaussian distribution. So this is the Gaussian function. So you can see here, if if we forget this term, so in our first slide we mentioned about the integral, I equals to minus I equals to integration from minus infinity to plus infinity e raised to power minus alpha square plus beta x dx equals to under root pi upon alpha into e raised to power minus beta square upon 4 alpha. So that term will give, it's like normalized. You can just try it. Okay. So the total area is normalized to 1 for any sigma. So if we integrate minus infinity to plus infinity, it will just give us 1, which I was talking about. So you can check the my last video or formula on first slide. So taking the limit as the standard deviation. So now you can see one thing is common here. So if sigma tends to 0 for this particular uh, g sigma x, so we will get a delta x at here at x equals to 0. So this is the representation of this our Gaussian function, and we can here show that the Gaussian representation of the Dirac delta. Now let's see what we have discussed in this video. So first of all, we have this rectangular function which is given like this. Then we have this Gaussian function. So one thing was common in that we tried that the integration of from minus infinity to plus infinity is 1 for both these cases. So we uh, did limit sigma tends to 0 r sigma x for rectangular function, and limit sigma tends to 0 g sigma x minus a for this Gaussian function. We will get a Dirac delta function. Okay, so fundamental properties of delta function is that if we integrate this delta function from minus infinity to plus infinity, we will get 1. Now we discussed about one of the shifting properties. So this fx, we said this fx is a continuous function. So fx is del x minus a dx. Here integration is minus infinity to infinity. It will become fa. Now a ramp function t sigma is given like this, and Heaviside function is given by uh, this, and connection between Heaviside and ramp function is limit sigma tends to 0 t sigma x, and the derivative of this Heaviside function will give us a delta function delta x minus a. So if I want to write it in terms of Dirac delta function, a ramp function in terms of Dirac delta function, so I will write limit sigma tends to 0 d upon dx, derivative of t sigma x with respect to x. That will give us Dirac delta function. And the discontinuity rule, so if sigma dash x has a, so let me make it more generalized. So if we have a function which is discontinuous, uh, so its derivative will be will contain the Dirac delta function like this. Okay, so this is all about today's video. So you can comment about anything. If you don't understand, you found something fishy or anything, you can just comment. Thank you so much for listening me.